Hi, welcome back. In this lecture, I want to introduce multi-qubit systems. In particular, I want to talk about how to apply circular notation to multi-qubit quantum system. And then I'm going to go back to a concept that we talked in the previous module, that is entangled and separable states. That is something that we can achieve when we use multi-qubit systems. So far, we have been work on a single quantum gate circuit that allow us to rely on quantum phenomenon, that is the superposition. When we use a multi-qubit system, so for instance 2-qubit, 3-qubit, then a second important quantum effect can be used, and this quantum effect is the entanglement. So let's start to define a quantum multi-qubit system, and what we can look at is a register that is composed by n qubit. As with the conventional bits, a register of n qubits can be used to represent one of the 2 to the n different values. So for example, a register of 3 qubits in the state 0, 1, 1 can represent an integer value of 3. When talking about multi-qubit registers, we describe the decimal value that the register represents in the same quantum notation that we use for a single qubit and the cat notation. Whereas a single qubit can encode the state 0 and 1, a 2-qubit register can encode the state 0, 1, 2, and 3. Let's see how this can be achieved. So for instance, the 2-qubit system, the first state is in 0 and the second state in 0. This will represent our state 0. 2-qubit system where the first qubit is in 1 and the second qubit is in state 0. This will be used to represent the state 1. If the second qubit is in state 1 and the first qubit is in state 0, this is going to be used to represent the state 2. And finally, if both qubits are in state 1, this will be used to represent the state 3, sorry. So you see that using this 2-qubit, we can represent 4 integer value and these are going to be the state of our 2-qubit system. So this is the circular notation for a multiple qubit system. So we seen this before, so we don't care much about this now. So what is interesting now are these 2-qubit system. As I told you before, if we have a 2-qubit system, then we can have a 4 state from 0 to 3. If we have a 2-qubit, then we can represent 8 values. As we saw in the 1-qubit system, we allow for the superposition of state. So wherever you see here a circle filled, there is a probability to observe that state after the measurement. So if we take this example, we can observe state 0, 1, and 3 after measurement, but no the state 2. So what we saw in the case of a 1-qubit is also applied here in a multiple qubit system. So to summarize, to represent this kind of superposition of n qubits, we use a separate circle for each of 2 to the n different values that an n-bit number can assume. So for a single qubit, there are only 0 and 1 state that can be represented. For the 2 qubits, we can have a 4 state from 0 to 3. And for the 3 qubits system, we have 8 state or 8 values. And this can be from state 0 to 7. We saw before that when we have a multiple qubit system, we can represent it as as a combination, that is the tensorial product of different qubits. In this case, we called such a system separable. This is, for instance, a case that is separable. For instance, the 3-qubit register superposition of state 0, 2, 4, and 6 can be expressed in terms of each individual qubit state and the tensorial product that we use to combine a quantum system. So if we take the tensorial product of this qubit, we can obtain this multi-qubit system. So this is an example of a separable system. So we have the single qubit, and then we applied a quantum gates to each single qubit, and then we measured the state of the multi-qubit system. So how this is going to work? So here there is nothing. So what you do, we assume that is just an identity matrix. Here there is an Hadamard gate. They put in superposition here another Hadamard gate. So we apply this operation to this initial state of our qubit, and then we obtain a state for each of these qubits in a separate way. And then, since we want to have the values of the multi-qubit system, we take a tensorial product here between these three vector. We will see that the length of this vector is 8. And then if you do a measurement, if we apply the circular notation to this quantum system, we will take these results. And if you do a measurement, we will see that we can only observe 0, 2, 4, and 6 state. If our qubits do not interact with each other, we could employ multiple versions of the representation we use for a single qubit. In other words, we could use a pair of circles for 0 and 1 state for each qubit. Although this naive representation allows us to describe superposition of any one individual qubit, there are superposition of groups of qubits, so multi-qubit register, values that cannot be represented as a combination of single qubit state. So these are the so-called entangled state. An example of entangled state in circular notation is the following. So these represent a state of 3 qubits in equal superposition of 0 state and 7th state. Since 0 and 7 are in binary notation 0, 0, 0 and 1, 1, 1, we have a superposition of these 3 qubits being in state 0, 0 and 0 and 1, 1 and 1. So there is actually no way to write down circular representation that combine provide us this quantum state. So notice also that reading out of the 3 qubits always results in us finding them to have the same values. So 50% of probability will be 0 and 50% probability will be 1. We will come back later on this entangled state and how to achieve them with the quantum circuit that we haven't seen yet, but we will focus on the next lecture. So entangled multi-qubit state cannot be described in terms of individual description of a single qubit and then taking a tensorial product to combine it. The entanglement link is only describable in the configuration of the all multi-qubit register, since we cannot use a single qubit and then combine. It turns out that it is impossible to produce entangled states from only single qubit operation, and we are going to see in the next few lectures some multi-qubit operation to act on a multi-qubit system and achieve entangled states. So as in a classical case, we can combine different qubits in a multi-qubit system, and we can also obtain the so-called qubit if we combine 8 qubits. So we know that if we have n qubits in circular notation, then we will need 2 to the n circles. Our multi-qubit circle notation consider each qubit to take a position in n bit string. So that means that if we have n quantum bits, then will be 8 bit string. So it's convenient to label each qubit according to its binary value. So in this case, we're going to use the hexadecimal to the first state, and then we have the second qubit, then the third qubit. And then notice that we are going to use a power 2 in hexadecimal notation. 1, 2, 4, 8. Then it's going to be 16, that in hexadecimal is 1. Then 32, 64, around 28. So we can collectively refer to a register of 8 qubit as a qubit. So this is the last slides, and talk to you soon.